All right, welcome back to Multigrid Methods. Last time we were talking about the failure of the Galerkin condition and how one could still rescue a convergence result for the two-grid method and for the W cycle algorithm, even when the Galerkin condition failed. And we did this in the context of where we had an alpha weak convergence, or sorry, an alpha weak approximation for our method. So that's a weakened approximation condition. So recall the first thing that we started out when we were analyzing the multigrid methods was analyzing it whenever we were assuming some fairly strong assumptions where we were assuming that the strong Galerkin condition held and also the first approximation, or sorry, strong approximation property and the first smoothing property. Now we've relaxed that a little bit and we've even given up the Galerkin condition. We've relaxed the Galerkin condition and we're also relaxing the approximation property. So we said even in the context of having a weakened approximation property, like if we have an alpha weak approximation property, we can still prove the two grid algorithm converges. We can still prove that the W cycle algorithm converges. So we went through a fairly lengthy proof last time, namely this guy here, showing that the W cycle algorithm converges. But I said the problem with this convergence proof is that we require M to be sufficiently large to get this convergence proof. So if I fix the gamma target that I want for this algorithm, then my M has to be larger than 1 minus gamma to the p power, gamma minus gamma to the p power, divided by gamma minus gamma to the p power, all taken to the 1 over alpha power. So that's some number we argued. I think we said, I gave you a scenario where this was roughly 9. Um, and but if we add the added complexity of, these numbers here being not, um, well, a little bit bigger than 1, then we might be required for this theoretical result to have a fairly large number of smoothing iterations just to get convergence, to hit this target. So we want to improve upon that, and that's what we're working on with the next couple of results. So we already did this proof, so we're not going to go through it again. I argued that because we have because the error matrix for our method is self-adjoint, and the reason it's self-adjoint is because we were assuming that we had a balance pre and post smoothing. So then we can show that the error transfer matrix was self-adjoint for that case. Because of that, this convergence result can be improved. And the improvement just requires knowing something about how to expand these vectors V in a basis of eigenvectors for this matrix EL. So we know, what do we know about EL? Well, we know that it's self-adjoint with respect to this inner product generated by that matrix, and so we can show that that means that there's an orthonormal basis if we want, or at least an orthogonal basis of eigenvectors associated to this guy, and all of the eigenvalues are real. We can't say necessarily that the eigenvalues are positive in this case. We can if we make a few more assumptions, but that's not necessary. Uh, so if we use the last result and we expand V in a basis of eigenvectors from EL, then we can prove this result 11 without too much trouble. In fact, we did this in chapter 5 a lot a few months ago, a long time ago, and it's the same sort of idea. So I'm not going to go through that. I've left that as an exercise. Now, the reason there's room for improvement with that last result, the last W cycle result, is because M has to be so large to guarantee my convergence that that result isn't necessarily practical. So if I want to reach a fairly small target contraction rate, gamma, less than 1, I might have to make M pretty large, maybe 100 uh, smoothing iterations. And now that's fairly costly because the main cost of the multigrid algorithm is smoothing, and I have to do a lot of pre-smoothing and post-smoothing both. And so this can get fairly expensive. So what we want to show and what we will show with this improved result is something akin to what we called earlier the Bress-Hackbush result, and that is that we can get convergence um, with a symmetrized method. The Bress-Hackbush result was in the context of the V cycle method, but now we're in the W cycle context. But the idea there is that you could show that you had convergence for any number of smoothings, and you improved your convergence the more smoothings you did. And so that's exactly what I want to show with this result. Now, I said last time we had a number of technical lemmas that we have to have in order to prove the result. We have to have these in place. I've decided uh, reluctantly not to go through all the details, and that's just because the details are fairly complicated and I might even lose myself. So when I type these up 3 months ago, something like that, I was fairly comfortable with the results, and I'm quite sure that, and then of course, my buddy Abner checked the results fairly carefully. So I'm fairly confident in all of the details, but we're not going to check them here. The first thing we need is a Young's inequality. This is actually fairly easy, so this isn't the problem. A kind of modified Young inequality is what is first needed. The hard the hard part is this technical estimate which is needed. So I won't say too much else about it. It's a fairly complicated object that we encounter during the proof of the next result that we'll see. So we're going to encounter an object which looks like this. Um, and so I think this is a typo here. I think this should be a subscript K sub alpha. So I will check that, but I'm pretty sure that that's right. No, no, I think that's okay. I think it's actually okay. I was saying I was thinking um, this K alpha has to appear somewhere, so why isn't it there? This K to the alpha power appears, and this K sub alpha appears down here. So just keep in mind those are different things. And like I said, I'm already confusing myself. But in any case, we encounter some complicated object like this when we go through this improved analysis. And so we have to be able to control that whenever we put a certain quantity here in this first position. In particular, we're going to put the quantity delta squared there and then try to show that this quantity that we meet is less than delta whenever we put delta squared there, where delta turns out to be a fairly important constant for us. It's m divided by m plus m to the alpha power. Now, here's the point about this this object that appears. So, like I said before, it's nice to think about alpha as being something fixed. So, alpha is our constant that appears in our alpha weak approximation property. And as I said a few times, it's nice to think about this as being something concrete, like alpha equals a half. That's going to be the most important value for us. So, what is this constant here? Well, we're going to show that this is effectively our contraction rate, and we're going to try to show that um, this object that appears is less than a contraction rate that is nice. Okay, ultimately it's going to be less than delta. So what does that mean? So if it's less than delta, this m is going to be a fixed number which is independent of most everything. And then we're going to have an extra m to the alpha. And now the nice thing about this m to the alpha is that this constant or this number gets smaller as m gets large. Okay? As m gets large, m to the alpha gets large. So in this case, it's going to get large like the square root of m. That seems like it's not ideal, but it's not too bad either. So if we do 4 smoothing iterations, this is going to be 2. And so this number, whatever the heck it is going to be something divided by the same something plus m to the alpha, where this guy can be improved, okay, through smoothing. So this number here is very clearly going to be less than, or strictly less than 1. And so if we can show if we get a contraction rate like this is definitely contraction because it's a number which is less than 1. But the important point is that it improves or gets smaller as alpha gets larger. And so this tells us that if we can ultimately establish this is our contraction rate, then it improves, it gets better as m gets larger, and it holds as, for any value of m. Okay, we get a contraction for m equals 1, a contraction for m equals 2, and so on. Now, it might not be such a big contraction whenever m is equal to 1, little m is equal to 1, because this number might be like 100, so it would be 100 over 100 plus 1 in that case. So 100 over 101, that's a number which is fairly close to 1, so that contraction isn't so helpful, but we can improve it by making this larger and larger. And hopefully, the hope is that m is not so big, it might be 10. In that case, then we can improve it by a lot by making this guy, let's say, 4 or 9, something like that. We can dramatically improve this by making it dramatically less than 1. So I'm not going to prove this technical lemma. It is fairly complicated and fairly technical. It's a few pages long. It's all fairly elementary stuff, and it uses that improved Young inequality. But you can see it does take 4 or 5 pages of proof, and so we will skip that. So we're just going to put that in our pocket. Now, the one thing that we will need for this proof, this extra little bit, is something that I want to recall from earlier. In section 5.8, perhaps it is, we proved something called the Bress-Hackbush result. And this was an improvement on the convergence of the V-cycle method, showing that we gain an improvement by doing more smoothing iterations in the pre and post smoothing steps. And it used Richardson smoother, and so here are the details that we're going to need to extract for this coming proof. So if we use Richardson smoother, that's basically a smoother where we select the smoother to be 1 over the spectral radius times the identity matrix. Now, it's not exactly the spectral radius. It's a good approximation of the spectral radius. It's what we call an asymptotically tight approximation of the spectral radius. It only needs to be greater than the spectral radius, but less than some manageable constant, like really 1.2. It's fairly manageable, times the spectral radius itself. And if this happens for some fixed constant which is independent of L, then we can prove the following things that we need to prove. The first one is this complicated estimate here. That's not the one that we need, as I recall, or is it? We're going to use one of these two, but I just want to recall them to life here so that you can see what I'm going to be using. I forget which one I'm going to be using in the next proof. Is it going to be 23 or 24? So we're not going to prove this lemma. This was already proved for us, but once we get to that point, I'll flash back to this, and we'll see that we get this particular improvement. Okay, so let's put that in our pocket, and here's the statement that we're going to prove. So suppose that we have a symmetrized W cycle scheme, M1 equals M2 equals M. Suppose that we have the standard W cycle. Standard W cycle means P equals 2. We've been using the definition that W cycle means P is simply greater than 1, whatever that means. So V cycle is P equals 1, W cycle P anything bigger than or equal to 2. But really, in the literature, it's this object called the standard W cycle, which is exactly P equals 2. Now we're going to assume that our scaled Galerkin condition holds. This is not the typical Galerkin condition. This is that kind of broken Galerkin condition that we introduced at the beginning of section 5.9. And we're going to assume that the alpha weak approximation property holds A2 with some alpha which is between 0 and 1, not including 0 or 1, because those are limiting cases that don't make a lot of difference or sense. Now we're going to define K sub alpha as in 13. So this is this K sub alpha is what appeared in that technical lemma. Okay. And so remember, it was defined in some way based on K and alpha or some weird power of alpha. Let's go back and look at that. So 13, there it is right there. So whatever K is, you fix K, you fix alpha. Alpha is the number that you get in the alpha weak approximation property, and then from that you can compute this thing called K sub alpha. All right, and now K is going to be precisely equal to the constant that we get from our alpha weak approximation property squared times the Richardson constant. So this constant came right here. This is involved in that asymptotically sharp approximation or over approximation of the spectral radius by this thing called capital lambda sub L. So sometimes I'll call this the asymptotic spectral radius or the pseudo spectral radius, something like that. But it's not exactly the spectral radius, it's just something related to it. Remember, this is our notation for the spectral radius of A sub L, our stiffness matrix. All right, so that's our Richardson's constant. Now we're going to let M be chosen so that 15 holds. So what was 15? 15 is this guy here. Okay, so whatever we need to make that hold, it's chosen so that that guy holds. It's greater than the maximum of these two objects. So on one hand, I have something which depends only on the constants of the scheme and alpha, and here we also have, it could possibly depend on the size of M to the alpha power. So the number of smoothing iterations raised to the alpha power. All right, so that's M chosen to satisfy or so that 15 holds. Then for every L between 1 and L, capital L inclusive, the W cycle error matrix EL satisfies this inequality. So this is precisely the gamma that we were looking at previously. Or did I call that delta? What did we call that? Let's see. We called it delta, but we can call it gamma as well. In any case, this becomes our contraction factor. Okay, so there's our delta right there. We're going to try to establish that contraction factor. And as I said, this explains why this is an improvement to what I had previously. It's an improvement because now I can see that I get a better contraction factor the more smoothing iterations I do. And I see that I even get convergence for m equals 1, the m equals 1 case. So I get convergence even whenever m is equal to 1, but the convergence definitely improves as I do more smoothing iterations. So I could do um, 20 smoothing iterations and get a better contraction factor theoretically than if I do one or two. But I get convergence in any of those cases. All right, so the proof, it just relies on the technical lemmas that we had earlier. The proof is by induction, and so we're going to do induction in the following sense, in the following way. We're going to assume that we can establish or that we have the inequalities that we want at the lower levels. Then, so so that's our induction hypothesis. And then the induction step is going to be to show that this holds true for the next step. Okay. So I guess for some reason I changed back from delta to gamma, but that's fine. Um, we don't have to stick to delta or gamma. We can choose whatever we want. Now, in the proof of the previous theorem, so this goes back to the last class when we were proving the convergence of the W cycle method. We showed that the absolute value of this object here, VL is an arbitrary vector on level L. We showed that this object in absolute value is less than this piece and this piece. Now, actually, we showed this for generic P, but now we're fixing the P value to be exactly equal to 2. So if you flash back a few slides, we've already shown this. So let me see if I can nail it down where we showed this already. So somewhere about here. Let's see. Right here. Okay, so I got pretty close to it. We've already shown this as part of our previous work. All it required was the structure of the problem. It doesn't care about the size of gamma or anything like that. It doesn't, if we have gamma being of a certain size, we showed that, you can do manipulations until you get things which look like that. Now the gamma should be less than 1 for this to make sense because this thing here has to be positive, and of course that's positive. This is already going to be positive no matter what gamma is, but for this to make sense, we really need gamma to be less than 1. Now if I raise it to the p power, gamma is even smaller, and so 1 minus gamma is still going to be is still going to be positive. Um, in fact, it gets as this guy, if I'm to fix gamma to be some contraction which is less than 1, and I raise it to more or higher and higher p power, then this number gets smaller, and so 1 minus that number is going to converge down to 0. But in any case, we showed this in the previous result, and so there's nothing to do. We don't have to reprove that result. So, or sorry, I should say we showed it here. That's the induction hypothesis, and we showed this result previously. Now, in the result that we showed, I want to be a little bit careful. So we start off with V on this side, V sub L, but we end up with W sub L on this side. And what is W sub L? W sub L is defined as previously, it's just the error transfer matrix for smoothing raised to the m power times VL. So WL is VL times an error transfer matrix. Now, this is the error transfer matrix for Richardson's smoother. I guess there's not much more to say. Well, Richardson's smoother raised to the m power. Okay. So, what are we going to do? So, let's see. So, we're going to use A2 because we haven't used that yet, and we're going to use one of the estimates in this Bress-Hackbusch result, or one of the technical estimates that we needed in the Bress-Hackbusch result to prove the following. So what we want to do is now, remember this is our induction hypothesis. We need to show something which looks like this at the next level up. And so we need to start with an object which looks like that, right? And so somewhere we're going to encounter this object, hopefully, and then we're going to apply that result to hopefully get this guy to be small. So we start out with this estimate we proved last time and our induction hypothesis. So let's look at this guy. By A2, well, start with this, and A2 says something about the structure of this. Okay, so if you go back and look at how is A2 described, it says I can replace this object here by all that I see here. Okay, all this stuff, right? That's applying, that's what you get when you apply the condition A2. So that's precisely that. I'm simply taking this stuff here and I'm replacing it with all of that stuff. That's exactly condition A2. So I'm not going to go back and show you what A2 is. It's exactly that. This doesn't change. It's the same as it was. All right. So let's see if we can do a bit more work on it. Now, we need to use this thing 24. 24 was one of those technical results that we needed in the proof of the Bress-Hackbush result, and which I expressed as a lemma and said, this is what we're going to need one of these two. And I said, I don't know which one it is 23 or 24. So now I'm reminded it was exactly 24 that we needed. So it was this guy. So I need to look for something which is an A norm. Sorry, not A norm, but A times KLM times V. So this is exactly what we called in the current proof that we're working through, we called that guy W, right? So I need to look for something which is ALW, and this Euclidean norm squared divided by, hopefully we can find a division by rho L, the spectral radius. Okay, so let's see if we get those objects. So there we go. Here, looks like what we're looking to replace is that guy. Now, we don't quite have it as you saw in that estimate. We have it raised to the alpha power. So whenever we do our estimate from 24, it's going to replace all of that stuff with 24, but 24 raised to the alpha power. Now, right? So that's exactly what 24 is. Okay, so we're going to have this, but not exactly that. We need it to the alpha power. So since alpha is a positive number, this to the alpha power is less than this to the alpha power. Okay, so we can apply this 24 estimate. That's exactly what's appearing here. Now, all I do is uh, make the case that, let's see, do I do any other work here? So we've got a couple of combinations. This can be combined with this term here. Although, let's see, I have a V here. Maybe that V is a typo. Let's see. Let's go back to 24 because I think I may have a typo. No, it's okay. So this is VL. So it's VL, right? And then this here is WL, so I should get WL there. Okay, so it's correct. Now I claim that all of what I have here can be rewritten as a big old constant times VL times, well, the AL norm of VL squared. All right, so is that true? So let's go back for a second and look at how gamma is defined in 14. Because what I'm claiming is you can transform this exactly just through this expression. So I'm claiming it holds with equality. There's no estimates at all here. And let's see if you believe what I'm saying. So now I'm claiming that I can do that, but where I'm going to replace x with this number here. X is going to be defined as WLAL squared over VL in the AL norm squared. Okay, so I have to arrange things so that I get an X somewhere and then ultimately times this guy. Well, first of all, let's see if I wanted to get if I wanted to get this guy to be VL, how would I do that? Well, I would multiply by VL and then I would divide by VL. So multiply by I should say the norm. And so I'm going to get the division of the AL norm of VL squared. So that quantity is then going to be called X, and then I'm going to be left with VL out here. Okay, so that's looking good. All right, so now let's go back to 14 and see how that thing is defined. So 14 was this object here. So I have a beta. So whatever appears in front of beta or in front of x is going to be called beta. I just explained that that x is exactly what we have on in the last term. And then I'm claiming that we also have these 1 minus x to the alpha, x to the 1 minus alpha terms appearing. So let's just double check. We might not be so clear and it might not be so easy to double check all of this because I don't want to be flashing back and forth over and over again. So maybe I'll just say if you are careful about your algebra, you should be able to turn this object, which appears here, into this object. And I guess let's leave it at that. Where I've converted this object here to be this thing, which I'm calling, or let's see, this any objects which look like that, it's going to get converted into X. Okay, so let me say it's an exercise to turn this whole business into this. And now, as I said before, whatever object or whatever number appears in front of this ultimate object, which I'm going to turn into an X, is going to be what I call gamma squared. So that makes sense. And there's another gamma squared that appears out front. So that looks good. Now, so if I can show this, if I can really get this guy is less than this times that, then this is going to be my contraction factor that I want to show. But now I really have it because I have my technical lemma that I want to throw at things. Remember that technical lemma said that as long as I have this object here appearing on the right hand or the left hand side, I can say with certainty that that's going to be less than gamma, where, well, I think I used delta squared and delta, but we're now changing them to gamma squared and gamma. So that's basically it. We're going to employ that crazy technical lemma to conclude that really we have this guy being a true contraction. That number is less than 1, where gamma was precisely equal to this quantity here. Maybe I need to say that somewhere, that gamma is that. So let's see, did I say gamma? Oh, yeah. So I set gamma to be that parameter right there. So that is the essence of the induction proof. If we really have this less than that, then in our previous result, we showed that that implies this, and we don't really care what this gamma is. It just has to be a contraction. Then we're going to apply our alpha weak approximation. And finally, we apply that technical lemma that came before the Bress-Hackbusch result. I don't have a good name for it. It's just something that we used previously. Turns out I can reuse that to ultimately write this is less than some horrible looking factor times the AL norm of VL squared. Okay, and there's one other thing I need to check, and that is, does this thing which I define as X satisfy the condition that I needed for my technical lemma? It needs to satisfy X is between 0 and 1. Now, the reason why it satisfies that condition is precisely because of what we call the stability of Richardson's smoother. So we showed somewhere else that this number here is less than this guy. Okay, th so that's just a stability statement that we used previously, and I quoted it as a lemma or a theorem or a technical lemma somewhere. But it's for that reason, because we have a stable smoother, that x is between 0 and 1. And so that allows us to apply the crazy technical lemma to ultimately conclude this. So that's basically all I want to say about that. As I said or have indicated, there are a lot of really complicated technical details that I'm skipping over here. Once I decided to skip the proof of the technical lemma, then we kind of give up some of the fine-grained detail that we would have gone through. Normally, we're just kind of wave our hands and hope that everyone believes it. So if you do go back and check, I would be happy to hear if you find any errors or typos, but I'm pretty confident in the proof. So I will say it's a little bit different than one that we found in the literature. It's a little bit more solid. So the result is not new. The result comes from a book by Bramble. In that book, the actual computations and that technical lemma is really horribly done, and uh, I couldn't follow it at all, the proof, and I wasn't even sure it was actually correct. However, the proof that we established for the technical lemma, that crazy technical lemma, um, uh, the previous result is, I think, correct, and so I'm quite sure that, well, as certain as I can be, that the result is ultimately correct. But there are a lot of details to go through that we simply didn't because they are complicated. All right, now I want to point out an open problem in the multigrid literature. So now I've gotten you very close to the front lines of multigrid, right up to a big open question that if you solve it, you'll be relatively famous in the multigrid community, and that is we don't yet know if the standard V cycle under condition G3 and A2 is convergent. Um, no one has been able to prove that. However, every time we do a simulation with the cell-centered finite difference case, which we're going to get into in chapter 7, we usually always get convergence with the V-cycle method. So it looks like we have a lot of circumstantial evidence to suggest that we have convergence. It's just that no one has been able to prove it. So the V cycle, the W cycle, certainly we have the previous two results. We have convergence, but it turns out the V cycle converges as well. We just don't yet have a proof for that. So if you could prove that, then you'll get your name on a plaque somewhere and you'll be quite famous. All right, so the next topic that we want to talk about is precisely an application of the theory from section 5.9 to something called the cell-centered finite difference method. I've been really excited about this chapter. It's been in the works since maybe September. And my first couple of iterations at this chapter didn't work out so well because the theory I was using wasn't quite right. And so I worked on it for a long time. And now it was well known what the theory should be uh, in this book by Bramble and these sets of notes, the set of notes by Bramble. It's just that I didn't feel like maybe that was the whole story. It turns out if it's not the whole story, it's most of the story. So I got myself on the right path and I got the right theory down, which now became the theory from chapter or section 5.9. Now I'm really excited to show you what I've learned and what we can say about the convergence of the multigrid methods when applied to the cell-centered finite difference method. So the first thing we have to do is more or less completely define what we mean by the cell-centered finite difference method. Most of you have never seen this topic before, this concept, and so let me spend a little bit of time talking about that. So this is the part one of three. So I imagine the slide deck is going to have three parts, or the slide deck is going to come in three parts. Right now, we're going to spend part one talking about the basic ideas of the discretization method for the cell-centered finite difference method, as what the stiffness matrix looks like and how smoothing goes, et cetera, et cetera. Right. So the problem that we want to solve, first of all, is the simplified one that we've been working with all along, and that is the one-dimensional boundary value problem, two-point boundary value problem uh, in one dimension. In fact, we'll use the simplified domain omega equals 0 to 1 because it doesn't make sense to make the problem any more complicated than that. And we're going to set u to be 0 on the boundaries, right? That's the Poisson problem. And it satisfies Poisson's equation in the interior. So u equals 0 on the boundary minus u double prime equals some given function f in the interior. And we're also going to look at the 2D analog of this problem. And furthermore, I should say, we're also going to, in this chapter for the very first time, not for the first time in history, but for the first time for us, we're going to look at the case where we have non-constant diffusion coefficient. So non-constant diffusion means that we have some function, some coefficient d here, which is a function, which is not necessarily a constant. It has to be a positive, it has to be a function which is everywhere positive. Um, but I won't say too much more about it than that until we come back to it. We will address a more complicated, more interesting problem than what we are used to in this chapter, so I'm excited about that as well. But that's the main idea. We're really interested in first this problem and then later on this problem. Now, the details of the cell-centered finite difference method are quite a bit different than the finite element method that we've reviewed previously. And I think in chapter 3 is where we introduced this concept of the finite element method, and we said, well, the finite element stiffness matrix that you get is entirely the same as something called the finite difference stiffness matrix, or it can be related in a clean and simple way. Now, however, when we do this so-called cell-centered finite difference method, it's different than the standard finite difference method, and it gives us a different stiffness matrix, as we'll see. Well, there are some things that don't never change, and the thing that doesn't change for us, at least, is when we start out defining the sizes of the grid, we're going to give it this hierarchy of numbers NL. And related to NL is going to be this mesh spacing called HL. Now, HL, as usual, is defined as 1 over NL, okay? Or it's fairly common to define it that way. But now notice that NL, unlike the finite element case, is going to have an even number of elements, except for possibly L, little l equals 0. So this Q is any number that we want to choose as long as it's an integer, positive or a non-negative integer. Let's see, yeah, positive integer is right. So Q is any positive integer. So this could be 2, 3, 4, 5, doesn't matter. And then, so you can see that n sub 0, this guy is going to be 1, so is precisely equal to Q. So which is what I said there. However, for L bigger than or equal to 1, we can see clearly that this is some number times a power of 2, and so NL is always even in that case, right? So that differs from the finite element setting where we always had odd numbers for the sizes of our grids. Let's define, now that we know what HL is, let's define what we mean by cell-centered points. So let me go to this diagram first, because once you see the diagram, it's fairly easy to see what's going on here. Now, here's our physical domain, 0 to 1, or 0 to 1. So here I'm showing a coarse grid, and here's a fine grid, where Q is equal to 2. So that would be the number of elements in the level 0 grid. Okay, so Q is equal to 2. How would I get to the next level grid if I refine it? Well, I just use my formula. NL is equal to Q 2 to the L. Okay, so for L equals 1, if Q is really 2, then this is going to be 4 for the next level up. Now notice that the cell-centered points don't appear at these cell vertices the way they used to. The vertex points that we saw in the usual finite element grid, and even in the finite element method, were at these edges here. Okay, so for example, this is exactly at the point 0, exactly at the point 1. And what are these values here? So this would be 1/4, 1/2, and 3/4. There aren't any grid points there. We're going to use the so-called cell-centered grid points, which are in between 1 and 1/4. So this is at an eighth. And this next grid point is going to be between 1/2 and 1/4, whatever that number is. And this one's going to be between 3/4 and 1/2, right in the dead center. And it's called cell-centered because the grid point appears in the middle of the cell. Okay, so we call this a cell, and the grid point appears in the middle of the cell. Now we also have, for the cell-centered framework, we also have these grid points which appear on the outside of the domain, and these are called ghost cells. Okay, we always, at least for the theoretical purposes in the book, we always denote the first cell-centered grid point, or the what I'll call the left ghost cell, is always has the index equal to 0, whereas the right-hand ghost cell is always has the index NL plus 1. So in this case, L is equal to 1, so it's N1 plus 1. And this guy here is N0 plus 1. So that's the right-hand ghost cell. The left-hand ghost cell always has the index 0, but the right is NL plus 1. Now let's go back. The cell-centered grid points are defined as XL comma I is HL times the quantity I minus 1/2. So let's look at the first one. As I said previously, on this grid here, H1 is equal to 1/4. Okay, so H1 is 1/4. That's the size of that grid cell. And it's also going to be the spacing between any cell-centered grid points, and even the spacing between an interior grid point and a ghost grid point. Okay, so H1 is going to be 1/4, but we're going to try to get these, we're going to try to make a definition so that the grid cells, or the grid points, appear in the centers of the cell. All right, so let's see if this works out. For the first one, I is equal to 1, so this is going to be I minus 1/2 times times HL, which is 1/4. So this is what? I minus 1/2 is going to be 1/2 times 1/4 is going to be 1/8, right? And so that's exactly this point here. It's between 0 and 1/4, so it's exactly 1/8. So that's the appearance of the first grid point. The second cell-centered grid point is here, halfway between 1/2 and 1/4. Okay? So we keep up that type of way of defining this, even if the grid size has a finer mesh spacing. So in this case, this is showing a coarse and a fine grid where N0 is equal to 4. In other words, Q is equal to 4, and then N1 is equal to 8. And you can see, again, the cell-centered grid points appear halfway between the cell. Okay, so that's why it's called cell center. So that explains this weird definition of these cell-centered grid points. Notice that in our counting, we also include 0 and NL plus 1. So 0 and NL plus 1 are precisely the ghost cells. Now the set of cell-centered grid points is denoted by C sub L, and it contains all the grid points, cell-centered grid points, including those two ghost points, okay? 0 and NL plus 1. Now the 0 ghost cell always is to the left of 0, and the right hand ghost cell is always to the right of 1. Okay, and they're outside our usual domain 0 to 1. Now, distinct from this is going to be useful for us to denote something called the set of interior cell center points. And so the interior cell center points is going to be denoted with this 0, which means interior. Okay, so this guy is defined as just the ghost cells or just the ghost points that are strictly in the middle. Okay, so it would just be these 4 ghost cells in this case, not including the, I'm sorry, just strictly these cell center points, not including the ghost cells. Okay, so I said that wrong. Right? So the interior cell center grid points are the same as this, except we're not going to tag along or tag onto the set the ghost points. So these leave off the ghost points. Now the vertex points are kind of defined as usual, except we're going to use this weird notation to define them. Notice that with the cell center points, we use the subscript Li to denote the cell center points. So this is x11, x12, x13, and x14. But what about these points here? Those can be useful to us as well. Those are what are called vertex points. But instead of using the notation x11 for this guy, we're going to use the notation xli plus a half, where I goes from 0 to NL. So in fact, if you look at how this definition works out, the first vertex point here is going to be x1 a half, and then it's going to be x1 3 halves, and x1 5 halves, and x1 7 halves, etc. So the vertex points are numbered a bit funny. So notice that in the index they have a plus 1 half, but there's no plus 1 half or minus 1 half in this definition. That's because we want things to jive with what we have for our cell-centered definition. And this guy, we pair up I, with this offset I minus a half. Okay, so now we're going to define something called the disjoint grid cells. So the grid cells are nothing more than this set where the cell center grid point sits in the middle. Now, I'm going to take this, this is usually called a cell, this is a cell, this is the next cell, but I'm going to define this in such a way that when I take a union of these guys at the end, I get precise, or so that they're disjoint, and when I take their disjoint union, I get the interval all the way from 0 to 1. So the way I do that is to make these guys disjoint, but so that I get the full interval more or less, is I'm going to take these to be half open. So it's going to be open on the left and closed on the right of the cell. And notice that this goes from the vertex on the left to the vertex point on the right. So for example, this cell here goes from here up to there. Okay, so that's the second cell. And the third cell is that. So it's half open. It's open on the left and closed on the right. And then finally, the fourth cell looks like that. Remember, the cell center points are always in the middle of the cell. Okay, so that explains all of our definitions, right? All of those in terms of a picture. Now, when I take the disjoint union of K, I don't get the point over here, but that's okay because, you know, 1 point amongst friends is not a big deal, especially when we're dealing with Lebesgue measurable functions. How you define functions on or at a single point or a set of measure 0 is not so important. Okay, so we refer to the cell-centered multigrid uh, meshes as being nested grids. So we'll commonly refer to these grids as being uniform and nested. However, what you should see here, which is distinct from what we had previously whenever we had vertex-centered points or vertex-centered finite difference. So these points in this mesh, okay, so this is our 0 level mesh, don't line up with the points in the mesh above it, right? Or in the level just above. So notice that if we really did have these guys embedded, then this mesh point would go to here, and this one would go here, and this guy would go here, right? So there's something off if we want to call this nested, right? So this point isn't the same as that point. It's not the same as this point. It's somewhere in the middle. And in fact, this cell-centered point doesn't appear as a cell-centered point in the grid just above it. Okay, so that's an interesting fact, but we're still going to call these meshes uniform and nested. And that's because, well, if you look at it, if you'd like to look at it from the point of view of the vertex centered points, the vertex centered points are nested. So this vertex here is in the vertex, or is a vertex up here. Now, we do create a new one here. This vertex point is the same as this one. This one is new. This vertex point goes to this vertex point, but this one is new, etc. So it still has a nested structure to it, but it's not exactly the same nested structure that we had previously in the vertex center case. There are two equivalent ways of viewing functions that are built upon these cell-centered grids that are going to be useful for us. So let me give you a quick picture what these two versions look like, and then I'll come back to the actual definition. So of course we have these things called cells. They go like that. There's this first cell, second cell, third cell, fourth cell on a grid that has 4 points. So we can view grid functions in two ways. Number one is we can view a grid function as being a function that is defined by its values at the cell center points. Okay, so for example, that grid function might look like that. And you can think about maybe I'd like to connect those things together using a piecewise linear curve, something like that. Okay, and I've even added values at the cell at the ghost cells as well. Okay, so we really have a function which might look like that, right? But now that isn't the only way that I could view a function. And it turns out, or at least the only way that's going to be useful to us. Another way of viewing this is I could say, well, let's just define a piecewise constant function, which is defined as a function that over each grid cell is just some constant value. So there's its value on the first grid cell. There's the second on the second cell. Value on the second cell, the value on the third cell is up here, and the value down here. And so I can see two different ways of viewing the same information, right? And so the one is going to be called, the first way is just going to be called a grid function. The second way is what I'm going to refer to as a piecewise constant function. Both are going to be useful to me in my analysis and for the definition of these methods. Okay, so let's go back and define these things carefully. So the piecewise constant grid functions are functions that are just regular functions. They're not going to be continuous anymore, obviously, because they're piecewise constant, such that when I restrict their values to the grid cells, I'm just going to get a P0 function, just a P0 function. That's a polynomial degree 0. That's a constant. Okay, so it's just constant on each grid cell. The space of cell-centered grid functions and the space of interior cell-centered grid functions are defined as follows. So the cell-centered grid functions, or what I would yeah, these are the cell-centered, are just functions whose domain are the cell-centered grid points, CL. And for each cell-centered grid point, I'm going to assign a value in R. The interior ones are exactly the same, except that instead of using all of the cell-centered grid points, I only use the interior grid cell-centered grid points. For each interior cell-centered grid point, I'm going to assign a value in R. Okay, so you, I showed you this function or function which looked like, was from that class, and I showed you its relative or um, closely related relative from the grid function community or the grid function world, I guess. Now, I also going to define these objects called homogeneous Dirichlet cell-centered grid functions. So those are different than either this one or this one, in that it's going to be a function that is going to be defined on this larger set. So this larger set has the ghost cells in there as well. Okay, so it's going to be a function that has values of the ghost cells, but those values of the ghost cells are going to precisely be equal to negative the value at the next at its next neighbor. Okay, and same with this guy. The value at this ghost point is going to be equal to minus the value at its let's see, that this is technically true, but maybe I would rewrite this as, maybe I put the NL plus 1 here and just NL here. It's technically true as it is written, but I might rearrange this. So the idea here is that the value at the ghost cell is going to be equal to minus the value at the first cell. And like I like I said, I probably will rearrange this to be a little bit different, but the idea is the same. Minus the value at the ghost point is equal to the value at the last grid point. And I'll show you what this looks like in a picture momentarily. These are the space of homogeneous Dirichlet cell-centered grid functions, a very long defined object there. Now, it turns out in an obvious way, or maybe it's kind of obvious to you, I can identify these two spaces. What I mean by identifying these two spaces, this is the space of interior cell-centered grid functions and the space of homogeneous Dirichlet cell-centered grid functions. So if you give me any function from this one space, I can show you a companion function from this space. And I'm going to show you how to do that momentarily. How to relate these two spaces in what's called an identification. Now, one more thing I want to say. For grid functions, it's common, instead of saying a function of a grid point, it's just most common to say, I'm going to extract this number down here and use it as a subscript. Okay, so this means its value at the grid point, but I'm just going to use two subscripts to denote that. So for example, v11 is its value of the function v1 at the grid point 1, 1. The other piece of notation, so that's notation. The other piece of notation that you should know is what is called a characteristic function. So a characteristic function for a set A is a function that's equal to 1 if x is in the set A, and it's equal to 0 if x is outside of the set A, in the complement of A. Okay, so that's a fairly standard function called a grid function. Now I'm going to define what I mean by a basis for these piecewise constant functions. So for the basis for the piecewise constant function, I have to be able to take any piecewise constant function and reconstruct it through the basis as a linear combination, right? So basically, when I say this is a basis, I'm making a claim that it is a bona fide basis, right? I'm going to first call it a basis and then later on show that it is a basis by proving that it is a spanning set and that it is linearly independent. And I'm not sure why that is not bolded. typo maybe. So I have, yeah, I think this should be bolded as well. In any case, so I'm going to define the basis for the piecewise constant functions. And the basis for the piecewise constant functions is just going to be functions that are one outside the cell of interest. Okay, or did I say that right? Should be zero outside the cell of interest and one on the cell of interest. So they're just characteristic functions for each cell. Okay, so how many cells do I have? I have J going from 1 to NL cells, so I'm going to have a basis with NL objects in it. Now, how can I define the grid function basis? For the grid function basis, I'm just going to define this in the way we've defined these things before. So it's going to be the set of grid functions that are in this space CL0. So they have to have these homogeneous Dirichlet conditions associated to them. And otherwise, it's just the grid function that has the property that when I evaluate the grid function J at grid point I get the Kronecker delta symbol, delta ij. Okay? Now, if those are my two bases, then because they have exactly the same number of elements in them, exactly the same number of elements NL, your NL number, then that means if they're really bases, which I'm claiming they are, then the dimensions of these two respective spaces have to be equal to NL. So this is left as an exercise to show that those two objects give a bona fide basis. Now, I'm going to come back to this next time. So here's where we'll start. But I want to show you a picture of what these function spaces look like. Now, this function here, this grid function here that has these 6 values, is this guy in this space CL0? Well, answer is yes, because it's a grid function. And this point here at this ghost cell is equal to minus its value at the first cell-centered grid point. Same with this guy. Its value at the right-hand ghost cell is equal to minus its value here. Okay, now I made a claim earlier that said that interior cell-centered grid functions can be identified with homogeneous Dirichlet cell-centered grid functions. That's for one reason. One reason why that's true is because they have exactly the same number of degrees of freedom. So for example, if you give me this grid function, this interior grid function, that doesn't have points defined out here, how could I come up with a unique function from this space which has values at the ghost cells? Well, it's pretty easy. If I have an interior grid function, then I have values at these 4 points, but I'm able through a very easy prescription to set this value so that it makes it a function from this space. I just set it to be equal to negative the value at the first grid cell. And likewise with this one. For this grid cell out here, I'm just going to set it equal to its value minus its value at this last cell center grid point. So it's easy to see that I can make an identification between the interior grid cell center grid points and this function space called the homogeneous Dirichlet cell center grid points. Here's another question. Can I also make an identification between functions from the space of piecewise constant functions to any of these two spaces of grid functions? And the answer is yes, I can do that as well. So that's pretty easy. If I have an interior grid function that's given by these 3 or 4 values here, then the way I define a piecewise constant function is I'm just going to say, well, on the cell associated to this grid point, I'm just going to set it equal to that value all the way across the cell. And for this grid point here, I'm going to look at its value, the value of the grid function here, and just extend its value all the way across the cell. Same here, and same with this guy. So I can see that there's an easy identification. VL is really the same as CL0 because I can identify it, and CL0. Okay, so there's this 3-way identification between these functions. So I can either view a function as being an interior cell center grid point, cell-centered grid function, a homogeneous Dirichlet cell-centered grid function, or a piecewise constant grid function. All of them have exactly the same dimensions, and L in particular. They have different, this one has a different basis from these two. These two can have the same basis, this one and this one, but I can still make this identification. All three of these spaces are really the same, but they're different in different contexts and will be useful to us in different ways in different contexts. So that's where I'm going to stop. Next time we'll come back to this point that I want to make about identifications, which I think is actually fairly clear once you see this picture here, how these identifications may go.